Okay, today let's discuss about the flame atomic absorption spectroscopy. Let's look into the content of this video lecture. Content contains introduction about the flame atomic absorption spectroscopy and what is the principle involved in flame atomic absorption spectroscopy and instrumentation, more particularly the components of flame atomic absorption spectroscopy. The components of a flame atomic absorption spectroscopy are radiation source, atomizer, and then uh, photomultiplier means monochromator recorder. And then types of flame atomic absorption spectroscopy, and then atomization. Let's go to the principle of flame atomic absorption spectroscopy. Ground state metal ions normally sample for the flame atomic spectroscopy is in metal ion containing solution. That means in a liquid form it is used. So metal ions in a solution are converted into atomic state by means of flame. And these atomic state metals absorb light at a specific wavelength, and a light of appropriate wavelength is supplied, and amount of light absorbed can be measured against a standard curve. Let's look into the one more that write a note on flame atomic absorption spectroscopy. The technique of flame atomic absorption spectroscopy requires a liquid sample to be aspirated. Aspirated means sucking the sample, and then aerosolated. Aerosolated means converting into a small particle size and mixed with the combustible gases such as acetylene and air. Here acetylene is a fuel, air will be the oxidant. Again acetylene is a fuel, nitrous oxide is the oxidant. The mixture is ignited in a flame whose temperature ranges from 2100 degree to 2800 degrees centigrade. During the combustion, atoms of element interest in the sample are reduced to free, unexcited ground state atoms, which absorb light at a characteristic wavelength. The characteristic wavelengths are element specific and accurate to 0.01 to 0.1 nanometer. To provide element-specific wavelengths, a light beam from a lamp whose cathode is made up of element being determined is passed through the flame. A device such as photomultiplier can detect the amount of the reduction of the light intensity due to absorption by the analyte, and this can be directly related to the amount of element in the sample. Components of the flame atomic absorption spectroscopy. Typical flame atomic absorption spectroscopy photometer consists of the following compounds: radiation source, atom reservoir, it's also called as flame atomizer, and monochromator and detector. Let's look into the halocathode lamp. A device features a sealed cylindrical gas tube with a quartz window and haloed cylindrical cathode paired with a tungsten and anode wire. The cathode is made from the analyte, while the lamp contains an inert gas like argon or neon under vacuum. Applying a voltage and current between the electrode generates a low pressure glow discharge within the cathode material. Let's go to the next slide. The next slide will take the role of inert gas components in halocathode lamp. So here, basic function of the gas in the tube is to bombard the cathode and vaporize the atoms from the cathode surface. For this, the gaseous cations are accelerated towards the cathode. The collision energy is sufficient to cause some atoms of the cathode to be transferred into the gaseous atom in a process called sputtering. These metal atoms are then excited by the collision with electrons and ions, thus emitting characteristic emission lights. The emission spectra of the cathode material includes several intense sharp lines due to transition between the excited state and the ground state, often called resonance line. Intensity of the resonance lines from the halocathode lamp increases the increasing current. As of now, halocathode lamp for over 60 elements are available. So if we are looking at the alternative to halocathode lamp, one can use electrode-less discharge lamp. It's called EDL. It contains a few milligrams of volatile element or a volatile compound such as halide along with neon or argon under vacuum in a quartz tube. On the application of voltage, a discharge is produced and the gaseous atoms are excited by the application of microwave field or radio frequency of typical frequency. As excited atoms decay to the ground state or to the other low energy levels, characteristic radiations of the atom is emitted. Radiation emitted by the EDLs are about 10 to 100 times more intense than for the corresponding halocathode lamp. The electrode-less discharge lamps are available for the many elements. However, their performance is not as reliable as of the halogen cathode lamp. Let's look into the atomizer. The purpose of atomizer is to provide the small portion of the sample in the optical path and convert it into a free neutral ground state atoms in the flame atomic absorption spectroscope. The flames are commonly used atomization. Flame atomizer. The atomizer assembly consists of two components, nebulizer and burner. In a typical flame atomization process, a sample solution are generally nebulized with the help of nebulizer, in which the sample in the form of solution is drawn in and is converted into the fine mist or an aerosol. The aerosol so produced along with the mixture of a burning gas and an accident directed towards the second component, that is a burner. Nebulizer is a device used to sample introduction into the flame. It consists of thermal vaporization and dissociation of the aerosol particle at a high temperature, producing a small particle size. Several nebulization methods are available. A few are listed below: pneumatic nebulization, ultrasonic nebulization, electrothermal vaporization, and hydride generation. Let's look into the first one, pneumatic nebulization. The concentric pneumatic nebulizer is a common type of nebulizer used in analysis. It features a fine capillary surrounded by the centric tube with a small opening near the capillary end. During the operation, the capillary is immersed in a sample solution and high pressure gas follows through the other tube using the Bernoulli effect. The gas stream aspirates the sample solution into the capillary, breaking it into droplets of the varying size. Two major types of nebulizer burners are used in the atomic absorption spectroscopy are premix nebulizer burner system and the total combustion burner. In the premix burner, the fuel and oxidants are mixed with the burner housing before entering the primary combustion zone of the flame. The analyte solution is aspirated using a nebulizer into the mixing chamber, where it combines with the fuel gas. The mixture of the aerosol, fuel gas, and the oxidant products are stable, noiseless flame, ideal for the analysis. Let's look into the role of monochromator. In flame atomic absorption spectroscopy, monochromators plays a crucial role in selecting the specific emission line while excluding the interface from the molecular band emissions and the non-absorbed lines. The interfering lines may originate from the filler gas in the halocathode lamp or a spectral emission of the sample components during the atomization. Diffraction gratings are commonly used as a monochromator in most commercial instruments. Detectors, flame atomic absorption spectroscopy employs a photomultiplier tube detector to analyze the wavelength of resonance line which fall in the UV region. However, the detector not only captures the absorption signal intensity from the resonance line but also radiation emitted by the flame, resulting in a combined signal intensity of uh, to isolate the absorption signal and eliminate the interference caused by the flame emission, a mechanical chopper device used. Let's look into the role of mechanical chopper in a flame atomic absorption spectroscopy. Okay. So in a flame atomic absorption spectroscopy, the mechanical chopper serves a critical role in eliminating interface caused by the flame emissions. Signal modulation. The chopper periodically interrupts the light beam from the halocathode lamp, certaining a pulsating or alternating signal. Isolation of absorption signal. By modulating the light, the detector can distinguish between the desired absorption signal IA and the additional radiation from the flame emission. Improved signal clarity. The detector process only the modulates the light from the lamp, effectively isolating and measuring the analyte's absorption signal without interface. Single beam atomic absorption spectroscopy. It consists a halocathode lamp, a radiation source, a flame as an atomization device, a monochromator, a photomultiplier detector, and a recording system. The halocathode lamp radiation is chopped to eliminate the background signal arising from the radiation emitted by the sample itself, focused on the atomic vapor produced by atomizer and then directed towards the monochromator where the atomic lines of interest are isolated. Here you can observe that this is the halocathode lamp radiation source and then this is the flame. Before sample is here, sample is aspirated, converted into a fine mist. It is mixed with the oxidant and fuel and then enter into a flame. In the flame, it is converted into a free atomic state, and the free atomic state analyte captures the specific wavelength from the halocathode lamp, and then it will go to the excited. When it is coming back, it emits radiation that is identified by the monochromator, and it is passed through a detector. In the detector, intensity of the analyte is measured. So when it comes to double beam flame atomic absorption spectroscopy. In this, two types of instrument. The beam from the halocathode lamp is split into two parts by a mirrored chopper, one half passing through the atomizer and other half around it. So the two beams are then recombined by a half silvered mirror and passed through the monochromator. The ratio between the reference and the sample signal is then amplified, fed to the readout display radar. It must be noted that a reference beam in a double beam instruments does not pass through the flame and thus corrects for the loss of radiant power due to absorption or scattering by the flame itself. Let's look into the sample introduction method. In flame atomic absorption spectroscopy, the accuracy, precision, and the detection limits of the measurements heavily rely on the sample introduction process. The goal of the sample introduction system is to consistently transfer a representative portion of the sample into atomizer. This process varies based on the analyte physical and chemical state. Physical and chemical state, solid, liquid, or gas, and the sample matrix, soil, water, blood, plant leaves, or etc. While introducing the liquid and the gaseous samples are straightforward, solid sample poses significant challenges. So interference In flame atomic absorption spectroscopy, interference refers to the chemical, physical, spectral effects that alter the intensity of the analytical signal. The three types of interference are spectral interference, chemical interference, physical interference. Chemical interference and their method of elimination. Chemical interference occur during the flame atomization due to ionization, dissociation, or the formation of low volatility compounds. These interference reduce the atomic population available for the measurements. For instance, calcium absorbance decrease in the presence of phosphate due to the formation of low volatility calcium phosphate. Such interference can be mitigated by increasing the flame temperature to decompose the interfering compounds or using releasing agents like strontium and lanthanum to react with the interfering species, minimizing their impact of the analyte. So here I'm showing in a diagram. In this diagram, the flame colors are different for different element. This is one kind of flame because of the element specific one. And here I am taking the oxidant and fuel and oxidant types of fuel and oxidants and their maximum flame and the maximum temperature attained. And then I'm taking the few applications flame here application I'm taking the flame photometers are widely used in quality control where a simple and quick determination of the alkali or alkaline earth metal is required. They have advantage of being significantly lower priced than most other atomic spectrophotometer. Biological or medical application. Notable applications are the determination of sodium, potassium, calcium, and magnesium in body fluids and other biological samples. Food industry determination of calcium and iron in beer. Suppose halocathode lamp of palladium, halocathode lamp of lead used as a used in the determination of lead and palladium analyte when we are taking in a flame atomic absorption spectroscopy. Okay, I will stop at this stage.